Okay, welcome to calculus class. In this lectures, we're going to learn how to find a composite function and also inverse function. So our main objective is to combine functions to create other functions using arithmetic operations. Also, we're going to learn how to find a composite function and also how to find inverse functions. So we start with the combination of functions. Here we said that if we have two functions, the two functions can be combined in various ways to create a new function, again, using arithmetic operations. So for example, here we have f at x equal to 2x minus 3. And also we have g at x equal to x squared plus 1. We can perform the following instructions of the following functions. For example, we can add the two functions together. We can find the difference of two functions or the product or the quotient. So first we start with the f at x plus g at x. We know f at x is 2x minus 3. G at x is x squared plus 1. So we add them together by combining the like terms. So x squared is by itself, so we write down the x squared. We have 2x by itself also, we write down the 2x. But minus 3 and plus 1 are like terms, so we can combine it. So minus 3 plus 1 will give us minus 2. Also, we can find the difference of the two functions. For example, f at x minus g at x. This will give us 2x minus 3 minus x squared plus 1. Here we can remove the parentheses. Since we have negative outside the parentheses of the right function, that's g at x, we can multiply negative by positive and also negative by positive 1. So multiply negative by positive x squared will give us negative x squared. Also multiply negative by positive 1 will give us negative 1. So this means we are going to change the sign at for g at x. So here we get 2x minus 3 minus x squared minus 1. Now since x squared is by itself, so we get minus x squared. 2s by itself, so we get plus 2s. But now we have minus 3 and minus 1, so that will give us minus 4. The same thing applies, so we can find f at s multiplied by g at x. So multiply two functions, and we just multiply each element by each one. So first I can start with the 2s. 2s times s squared will give me 2s cubed. 2s times 1 will give me 2x. Then minus 3 times s squared will give me minus 3s squared. Minus 3 times plus 1 will give me minus 3, because negative times positive is negative, and 3 times 1 is 3. Now 2s times s squared will give us 2s cubed, because if we have the same unit, we had exponent. Since s is only 1 for 2x and s squared is 2, 2 plus 1 will give us 3, so we get 2s cubed. And since the answer here, we don't have any like term, that will be our final solutions. If we have any like term, again, we are going to combine it together. Then next we have f at x divided by g at x. F at x is 2x minus 3. G at x is x squared plus 1, so we divide. Now, since we cannot cancel anything, that will be our final solution. So we also have the concept of calling the finding the composite function. So here we say we can combine two functions in yet another way, which we call the composition. So the resulting function is called composite function. So sometimes we may have a question in college algebra. Two functions will be given and they say find the composite of the function, or even it can be three functions. So the resulting function again is called the composite function. So for instance, we have an example here. If I have f at x equal to x squared and g at x equal to x plus 1, to find the composite of f with g, we write the f function outside, then the inner function will be g at x. Now, if I want to find the composite of g with f, then G function will be outside, and the F function will be inside. So here we have F, G at X. So the first thing we do, we write the F function. The F function is S squared. So anywhere I see X, I'm going to replace it with S plus 1 since G at S is the inner. So we end up getting F at X plus 1. And since F at S is S squared, then we are going to square S plus 1. So our final answer will be S plus 1 squared. Again, finding the composite of F with G, it means the F function will be outer function, then the G function will be the inner function. So simply, if I have F at X, anywhere I see X variable, I'm going to replace it with G at S function. So here we have S squared, and G at S is S plus 1. So I have only one X, so I'll replace it with S plus 1. And that gives us S plus 1 square. And normally we use the notation F open period and G. So F open period and G here means F composite G, or F compose with G. So this is the concept definition of a composite function. Here we say let F and G be a function. The function given by F composite of G at X is F at G at X, because G will be our inner function for F. Now G composite or composite by F means G will be outer function, F will be the inner function. So here we say that is the composite of F with G. F composite with G at X. Now the domain of F composite with G is the set of all X in the domain of G, such that G at X is in the domain of F, as indicated here. So here we can see that we have F function is the outer function. The G function is the inner function. So that will be the input. So the input, we have input to G. When G function perform it starts finish, the output of G, we give it as input to F. So that's why again, F is the outer function and G will be the inner function. And it can be the opposite. If we have G composite F, then in this case, F will be the input in the inner function. And whatever F do finish, we are going to give the output of F to G as its input. So let's see one more example here. So here a function F at S equal to 2s minus 3 is given. And also G at X equal to S squared plus 1 given. Now they say we should find the composite of F G at X, which means F will be the outer function, G at S will be the inner function. Or G composite F at S, which means G will be the outer function, then F at S will be the inner function. So to solve the A, first we'll look at the F function. F at S is 2s minus 3. So anywhere I see X in 2s minus 3, I'm going to replace it with G at S, which is S squared plus 1. So here we get 2x minus 3, S become G at S, because that's the input. The output of G at S will be the input for F at S. So since we know G at S is S squared plus 1, then we're going to substitute it. So we get 2s squared plus 1 minus 3. Then we simplify the equation. We get 2s squared plus 2 minus 3. We can combine 2 and 3, so our final answer will be 2s squared minus 1. So again, here we are looking for F composite G at X. So G at X output will be the input for F at X. Again, g at s is our inner function. So this means the function f at s equal to 2s minus 3. Anywhere I see s, I'm going to replace it with g at x because g at s is the input to f at x. So here we get 2g at x minus 3. Since g at x is s squared plus 1, then we substitute g at x with s squared plus 1. Then we simplify the equation. The next example, we have g f at x. So this means g is our outer function. F at x will be the input to g at x. So here we get f at x squared plus 1 because g at x is s squared plus 1. So when I write s squared plus 1, anywhere I see s, I'm going to substitute with f at x. And since it's s squared, then it will be f at s squared. So from here, we know the expression for f at s is 2s minus 3. So we get 2x minus 3 all squared plus 1. We can simplify this equation by opening the parentheses. We get 4s squared minus 12s plus 9. And we can use the perfect square difference formula. We square the first term, 2s squared will give me 4s squared. We square the last term, negative 3 squared will give me positive 9. Then we multiply 2 with 2s and minus 3. So 2 times 2s is 4s. 4s minus 3 will give me minus 12x. Then plus 1. Here we can combine 9 and 1. So our final solution will be 4s squared minus 12x plus 10. Okay, so let's move on to the inverse function. Now, the concept of inverse function is very straightforward. If a function is given, let's say f at x equal to s plus 1, and they say we should find the inverse of that function, all we need to do is to change x to be y and y to be x and solve for y. And that's the concept explained here. For example, we have function f and g, two functions f and g. We know that f g at x, which means s for each s in the domain of g. G at s is our inner function. And also we know g f at x will be s for each x in the domain of f, because f at s is our inner function or the input to g at x. Now, under this condition, the function g is the inverse of f, because we have g at s is the input to f, and here f at s is the input to g. So this means the function g will be the inverse of f. Now, also the same thing, the function g will be denoted by f to the power negative 1, which represents the inverse of f. So we can write f inverse of f at s equal to x. And also f inverse at 1, f at s also will give us x. So the domain of f must be equal to the range of f inverse. And also the range of f must be equal to the domain of also f inverse, or the inverse function of f. So again, that's the theory. But now let's try and solve one example. Since we know if we have two functions, g at x and f at s, if f at s is the input for g at s, and also g at s can be input for f at s, then we say the two f at s is inverse of g at x. And the concept is applied here. You have a function f at s equal to square root of 2x minus 3. They say we should find the inverse of it. So first I can replace f at s as y. So we get f at s equal to square root of 2x minus 3, and we'll replace it at y equal to square root of 2x minus 3. Now, anywhere I see y, I'm going to change it to x, and anywhere I see x, I'm going to change it to y. Then we solve for the value of y. So here y now becomes x, and x now become y. Then we solve for the value of y. So this is square root. When the square root cross the equal sign to the left, it will change to square. So we get x squared equal to 2y minus 3. Then from here, we can substitute y will give us s squared plus 3 divided by 2. Since 2 is multiplied by y, when you cross the equal sign, it's going to divide. Or we can divide the whole equation with 2. So we get s squared plus 3 divided by 2, 2y divided by 2. So 2 cancel each other. So y will give us s squared plus 3 divided by 2. So the inverse function has the form of, we have inverse function of f at x equal to s squared plus 3 divided by 2. And s always should be greater than or equal to 0. And if we plot the function, this is what we get. We can see it to be a mirror image. So f at s square root of 2s minus 3. Then we have the f inverse at x equal to s squared plus 3 over 2. And again, this is a mirror image, or they are symmetrical. So now if we like, we can check our result by evaluating the concept of composite function f and f inverse at x, and also f inverse at f at x, which will say the composite of f inverse and f, and also the composite of f and f inverse. These two should give us the same. So we plug in the values here. First, we know f function is given. So we write the f function down. Then we substitute with the result. So we get something like this because we know f is 2s minus 3. And then the inverse of f, the answer was s squared plus 3 over 2. Here also we know the inverse is s squared plus 3 over 2. Anywhere we see s, we substitute with square root of 2s minus 3. So when we solve this question, we will see that here we are going to cancel the 2 plus 3 minus 3 will cancel each other, and we get square root of s squared. Here also, when we open the parentheses, we'll see that square root and square will cancel. We get minus 3 plus 3 cancel, so we get 2s over 2. 2s over 2 will give us s, and also square root of s squared will give us x. So the answer, if the answer is the same, that is the composite of f and f inverse, and the composite of f inverse and f at x. If they are the same, then the answer is correct. So again, the steps of finding an inverse function. When you have a function, substitute x with y and the y with x, then solve for y. And that will give you the inverse of the function. Then if you want to check your answer, then find the composite of f and f inverse, and also f inverse and f. Both should give you the same answer. So now every function has an inverse function. But in fact, for a function to have an inverse function, it must be one-to-one. Remember we said a function, an equation is a function if the input can generate only one output, or the independent variable value can generate only one dependent value. So if it's not, then it's not a function. So that's the example here. We have a function f at s equal to s squared minus 1. They say we should show that this is an inverse function. Another way of showing if this is an inverse, another way of showing that this is a function is to find the inverse function of it. So here the question says show that the function f at x equal to s squared minus 1 has no inverse function. So another way of doing this is that if we solve the equation, we find out that if we have an input to the function, we can generate more than one output. Then it has no inverse function. And actually, it's not a function also. So let's try this problem. First, begin by sketching the graph of f as shown. We plug in 2, we have 3, -2, we have 3 also. So which means we have some points here. And we can plug some few points. We get this form. For example, we can plug 0. If I plug 0, I'll get -1 and also +1. So here we say that if f does not pass the horizontal line test, which implies that it is not one-to-one, and therefore it has no inverse function. So to check if a function have inverse function is to pass the horizontal line. Remember, to check if a function is a function or if an equation is a function, you have to pass the vertical line, which means you have to touch only once. This is a function, it's touching only one with vertical line. But when we check with the inverse, there's a place that you touch it twice. And still we can try to find it. So we have f at s equal to s squared minus 1. We want to find the inverse, so we substitute s and y. So we get s equal to y squared minus 1. Then we solve for y. Y gives us plus or minus square root of x plus 1. This means there are some inputs that when I enter the input, I will generate 2 outputs. So that's not a function. Because we say the last equation does not define y as a function of x. And so f has a no inverse function. But the actual function again is a function. The original function is y equal to s squared minus 1. It's a function. But this is not, because we have plus or minus. And there are some input values that can generate 2 outputs. So the inverse function is not a function. So again, wish everybody the best and thank you for your time. Again, these lectures we went through how to find the composite function and also how to find the inverse function. We found out that inverse function, if we want to find it, when we have our function, we substitute x for y and y for x, and then we solve for y. And a composite function, we make sure if we are finding a composite function of f, g at x, then g at s will be an input to the f. So anywhere we see x variable for f at s, we substitute with g at s function, and then we solve for it.